Yes, we have a few announcements as everyone joins. First, we are recording this session and it will be available in Whova, our conference app, within 2 weeks after the Congress ends. If you'd like to ask our speakers a question during the session, please use the Q&A area to the right of your screen. The chat window is where you can engage with other attendees. And we kindly ask that you keep your microphones and cameras off during the presentations and follow the presenter's lead on when to engage with cameras and microphones on. Looks like we're ready to get started, so I'm going to go ahead and hand it over to Susan.
Welcome to the landscape fire management session. We have a great lineup today. I am your moderator. My name is Susan Prichard, and I will just be giving the speakers a 10-minute warning with the 5-minute mark to hopefully have them in close to about 15 minutes so there's time for a Q&A. Really encourage all of you to save up your good questions and ask them in the Q&A section, or you can turn off your mute button and just speak up at the end. So without further ado, I'm going to introduce our first speaker. This is Stephanie Mueller. I hope I pronounced your last name correctly, or you can. And Stephanie is a spatial analyst with the Colorado Forest Restoration Institute at Colorado State University. Thanks for your presentation today, Stephanie.
Thank you. All right, are you seeing the correct screen?
We are still seeing your notes, and you can just go up to that display settings and change it to, let's see what it is.
Is that it?
You're all set.
Great. All right, so hello and welcome to my presentation, Fire Weather Drivers of Severity and Spread, Learning from Past Fires, Fire Patterns to Inform Future Wildfire Decision-Making. So this research and this presentation was part of a joint effort with Grand Canyon National Park and Northern Arizona University. So of course, it's well understood that fire is a critical natural disturbance and ecological process in the southwestern US. However, as we've all heard by now, ponderosa pine and dry mixed conifer forests have experienced increases in forest density and fire hazard throughout much of the western US due to changes in both land and fire management. And increasingly, large and severe wildfires have impacted these dry forests. So fires that contain these large patches of high severity have the potential to impact multiple natural, cultural, and social values on our landscape. So in response to changing climate and fire regimes, Grand Canyon National Park is seeking to expand upon previous research on weather and climate effects on fire and increase both the pace and the scale of forest restoration using fire within park boundaries by addressing the National Park Service Fire Management Leadership Board priority area of implementing research that assists in removing stumbling blocks and hurdles for implementing fuels treatments and managing wildfires for resource objectives. So, Grand Canyon actually has a substantial fire organization that typically manages numerous prescribed and wildfires annually, providing them considerable depth of resources and experience to actually manage these large and complex fires at the park. Each year within the park boundary, managers decide whether and where to use prescribed fire or allow lightning ignited fires to burn for multiple objectives or to suppress those fires. So when making these decisions, managers must consider a multitude of factors, including vegetation, topography, fire return interval, current field conditions, etc., as important drivers of expected fire conditions, and if they actually have those right resources that are available to manage these fires. However, wildfires are, of course, also affected by the dynamic weather and short-term climate conditions in the Southwest. So air temperature, moisture conditions, and wind all have a strong effect on fire behavior, fire severity, and fire spread at various scales, influencing fire conditions on the fire line. So within Grand Canyon's forest ecosystems, considering weather and climate, how can we better understand the weather and climate conditions under which fire behavior becomes either more extreme or can potentially help us achieve restoration objectives. So the challenge is to help predict if expected fire behavior will surpass thresholds of fire severity and spread that threaten ecological and social values of the park, while simultaneously identifying those conditions conducive to using fire to move stand and landscape conditions toward desired conditions and desired fire regions. Right, so specifically, this research aimed to model and provide predictions of fire severity and spread during variable weather conditions under which fire typically burns at Grand Canyon, and then provide those climate thresholds that affect fire severity and spread to inform which fires may be beneficial or incompatible with multiple resource objectives. So in doing so, we also aim to develop some tools or products that could assist fire management planning and implementation at Grand Canyon by quickly assessing risks and identifying conditions that are likely to affect fire behavior outcomes. Okay, so our study area, of course, is located on both the north and south rims of Grand Canyon National Park in northern Arizona on the Kaibab Plateau. And these red polygons you see here indicate the location of the fires that we analyzed for this study. So fortunately, Grand Canyon has had about 19 large multi-day fires between 2000 and 2018 that were actively managed for research objectives and had available fire perimeter data for us to analyze. So these fires burned a total of over 99,000 acres, and there were a total of 488 consecutive progression days across these fires. So these fire progression maps of the daily area burned were provided by the park and mapped for the 19 fires. So using vegetation data from Grand Canyon National Park, we decided to limit the analysis to areas burned within mapped ponderosa pine and mixed conifer forests only. Although there were some multi-day fires on areas burned that occurred in these other forest types, pinyon juniper, spruce fir, the data we had for these ecosystems was very limited. So we did not pursue models in these vegetation types. Okay, so fire severity data was derived for each fire using the continuous relativized difference normalized burn ratio, RDNBR. And this looks at the change between the pre-fire and the post-fire imagery while taking into account pre-fire vegetation cover. So this provides a more stable definition of severity across space and time and can be used more easily to draw comparisons between these different fires. So for this analysis, we obtained the severity data using the Google Earth Engine platform, using the code that Sean Parks et al. 2018 developed. And basically this code takes the mean cover value for a Landsat pixel at any one point over a date range of 1 year pre and 1 year post fire to produce the resulting fire severity at each pixel. And then in order to obtain our thresholds for our severity classes from the Google Earth Engine data, we were able to use 665 composite burn index plots that were measured at Grand Canyon in these fires that we analyzed. So we regressed those values against the RDNBR to find our corresponding severity classifications. So that was plots with CBI values greater than or equal to 2.25 represent high severity, and in that case corresponds to a value of 682 or greater. So here are the map results for the fire severity of the 19 fires analyzed. And I think you'll notice there are a couple of fires. The Big Fire, the Outlet, and Fuller Fire do have some very large patches of high severity fire. But overall, many of Grand Canyon's large fires have actually burned at pretty low severities, which is pretty unique for the region. So the data for the weather and climate was mainly downloaded from the Northwest Climate Toolbox. Other than wind speed, we got that from RAW's data. And all data, except for the wind speed, of course, was mapped at 4-kilometer spatial grid, representing the daily 24-hour average weather. Then after obtaining all of the underlying fire severity, vegetation, topography, and that climate data, we created a grid of points across each of the daily fire progressions. And this information was extracted at each data point. So each point represents a burn pixel with a unique combination of observed fire weather and physical characteristics on that burning day. So to analyze the data and create models, we used a gradient boosting machine model. And this is very similar to random forest modeling. So the final models we built for each ponderosa pine and mixed conifer fire severity and spread are shown here in this table, along with the cross-value dated AUC. So the AUC, or the area under the curve, is basically the measure of the ability of a classifier to distinguish between positive and negative classes. So in this case means whether or not our model correctly predicts a pixel is burned at high severity or not. And so the higher the AUC, the better our model is at correctly predicting whether or not fire severity will occur during these certain weather conditions. So for example, our ponderosa pine fire severity model has an AUC of 0.7. So it was able to correctly predict the occurrence of high severity fire at least 70% of the time. And in the case of the fire spread, since it's not binary like high severity or not high severity, we use different percentiles of spread days. So specifically analyzing each model's ability to correctly predict large runs at various threshold settings, specifically greater than the 50th, 70th, 80th, and 90th percentile of area burned at Grand Canyon National Park. So for example, the mixed conifer fire spread model, the AUC of 0.78 for a 75th percentile fire spread day means the model was able to accurately predict whether or not a fire was expected to grow larger than the 75th percentile on that day. So the climate, topography, and fire weather variables are those that best help us predict fire severity or spread in each ecosystem without overfitting our model or providing redundant information. So one thing we found in this process was that elevation, VPD, or vapor pressure deficit, and wind were consistently important predictors in every single model. So with this information and in consultation with Grand Canyon Fire staff, we created these fire severity and spread prediction tables to give Grand Canyon simple and effective tools to identify the expected fire severity and spread associated with daily weather conditions when managing a wildland fire incident. So these tables use past wildfire conditions at the park to provide fire staff with a quick but comprehensive assessment of expected fire activity during changing daily weather conditions on a fire based on current and predicted weather conditions. So as mentioned previously, elevation, wind, and VPD were consistently important predictors across all of our models, while also being generally accessible to obtain during an incident and also several days into the future for planning purposes. So because of this, we use this combination of these three components to capture the expected effects of weather on fire severity and spread in these two dominant forest types at Grand Canyon. So kind of briefly, to use these tables, you would assess your forecasted average daily weather conditions for wind and vapor pressure deficit. And considering your elevation, you would trace the values for the wind on the left and VPD at the bottom of the box where the values intersect. So the value in the box in the case for the fire severity table contains that expected RDMBR value, but really more importantly, the severity classification based on those thresholds for Grand Canyon. So in this example, if our average daily wind speed was expected to be 4 miles per hour and the 24 average VPD was expected to be 2 kilopascals, we could expect our fire to potentially burn with moderate severity, or at least right on that threshold between low and high severity. And then these histograms on the left and the bottom, we put those there to help inform the user where the model has the greatest strength to make these predictions based on when these conditions occurred during fires at the park in the past. So similarly, the boxes in the fire spread tables contain an approximation of acres expected to burn given the wind weather conditions and at the elevation that you are currently at. So these tables we created provide predictions of fire severity and spread during variable weather conditions under which fire typically burns in Grand Canyon National Park, and provides those climatic thresholds that affect fire severity and spread. So these models are not intended to represent conditions on the ground, nor forecast some sort of worst case scenario of potential fire behavior, but rather the average conditions under which fire burns at Grand Canyon National Park. So instead, managers should be using this resource when formulating a strategy before engaging in operations by identifying weather conditions that are likely to affect fire behavior outcomes as they have during past fires. So if my forecast shows that from day 1 to day 4 of a fire, the weather is trending towards these windier or drier conditions, it seems to me that sometimes between day 2 and 3, I should start reevaluating my management strategy, because we're starting to see a transition between the severity and spread thresholds. So I just want to mention briefly some limitations to our modeling, and especially using these prediction tables on the ground. So these tables are based on the effects that weather has on fire behavior and does not account for other physical processes that influence fire on the ground. So fuel arrangement, fine scale topography, future, or rather prior management activities. So this model and this tool are intended to capture a longer term average of potential daily fire conditions, and really probably have some limited use during extreme wildfire events. Second, these weather conditions represent daily average 20-foot wind speeds and VPD conditions across a 24-hour period. So they're not necessarily point in time observations. And then finally, this was developed specifically for the unique topography and climate of Grand Canyon National Park. And the efforts of Grand Canyon National Park's fire program have resulted in fire regimes where these large destructive high-severity fires have been somewhat rare in the park's boundaries. And because of this, this tool is really limited to Grand Canyon National Park and may not work as well in altered dry forest ecosystems across other areas of the Southwest. So using fire to meet resource objectives contains an inherent level of risk, because we're dealing with a number of unknowns and uncertainty in what the immediate future will bring. But in many cases, using fire is the most effective way to accomplish fuel treatments at a landscape scale. So the fire severity and spread prediction tables, therefore, were created to characterize fire severity and spread associated with daily weather conditions at Grand Canyon National Park as a reference on what to expect when managing a wildfire incident or planning a prescribed fire. However, National Park Service policy directs land managers to maintain natural environments evolving through natural processes minimally influenced by human actions. So the maintenance of natural conditions generally precludes mechanical forestry practices, such as thinning or tree removal in the park, and it's seen as somewhat socially unacceptable within the park as well. So managing wildfires for resource benefit can achieve fuels reduction and typically a level of restoration that points a landscape towards a desired future condition with relatively little upfront investment of time or money or direct human influence. So this research framework we discussed here provides important insight concerning the importance of fire weather factors in determining the potential fire severity and spread on the landscape. And these analyses also provide an important decision support tool for fire managers in the form of the severity and spread tables. So the fire severity and spread tables were created to characterize fire severity and spread associated with daily weather conditions at Grand Canyon as a reference on what to expect when managing a wildfire incident or prescribed fire. But this research has direct and immediate applications for fire planning, potentially across the greater Southwest with some work. All right, so that's it with my presentation. I would certainly like to acknowledge my coworkers, Andy Thode and Jesse Young. Also our contacts at Grand Canyon, Matt Embring, Christopher Marks, and Aaron Banwell. And of course, my own institute, the Colorado Forest Restoration Institute. So thank you very much. And if you have any questions, let me know.
We have time for just a short question if someone has them. There's none in the Q&A, and I'll wait just a brief moment. If I don't hear one, I have a burning question on that.
Okay.
All right. Okay. My main question is that oftentimes operations use past fires to predict fire spread and even severity. I was wondering why that didn't end up in your matrix of tables, looking at time since fire, since it was an important predictor variable as well.
Oh, you saw like they consider where they are on the landscape.
Yeah.
Yeah, we did try to consider that because Grand Canyon has areas where it's burned 5, 6, 7 times. And so we tried to use time since fire as a variable to capture that. But you know, there's a lot to consider there. What's really happening after fire burns, especially in an organization that allows so much fire.
Gotcha. Thank you.
No,
Okay.
it's definitely concerned.
Yeah, we should stop there, but thank you very much. Okay. All right. Our next speaker today is Jacob Levine, and he's a PhD candidate at the Department of Ecology and Evolutionary Biology at Princeton University, and is going to be speaking with us about high severity fire and industrially managed forest lands. Thanks.
Thanks so much, Susan. Thanks, Stephanie, for that really interesting talk. Let me just pull up my slides. All right, can everybody see this okay? I'm going to assume that's okay. Awesome. So yes, as Susan mentioned, I am a PhD candidate at the Department of Ecology and Evolutionary Biology at Princeton, but today I'm actually going to be talking about some work that I started as an undergraduate in Scott Stevens' lab at University of California, Berkeley. And specifically, I'm going to be talking about the relationship between fire severity and forest ownership in California. So I don't think I have to spend too much time convincing you that the increased fire severity that we've observed since at least the mid-80s in California threatens both ecological and social systems. As you can see here, I pulled a figure from Zach Steele et al.'s paper in 2018, showing that the proportion of total burned area in California and in each region that burned at high severity has increased since the mid-80s, as well as the core area of high severity patches. And the latter trend is really the most concerning because the forests in California, the trees in California lack specific adaptations to respond or recover following high severity fire. And so when we get these really large high severity patches, what can often happen and what we've observed happening in many places is a conversion of mixed conifer forest to shrubland. And you can see this in this picture, which I took when I was on a survey crew in 2018. This is in the Moonlight Fire. And pretty much as far as you can see, we have head-high ceanothus shrubs. And this being 12 years after the fire, we found basically no regeneration. Now, this conversion to shrubland is problematic for several reasons, primarily for carbon storage reasons, as well as for timber production, conservation of natural resources, and while being actively studied, possibly has some implications for biodiversity as well. And so there's been a lot of research done about what is behind the increase in severity. And I'm not going to cover all of this, although as Stephanie talked about, obviously a huge component is extreme weather as mediated by climate change. And I'm not going to talk a whole lot about that except for how we sort of controlled for it in the study. What I'm really going to focus on is the issue of forest management. Specifically, when we talk about forest management and fire severity, we're really talking about how forest management influences fuel structures. And so, as many of you know, this is sort of an issue that has spilled out of the scientific realm and has become a really large debate, emotionally charged debate often, that's played out in political op-eds, has been taken the mantle by politicians themselves, and has generally kind of become a very emotional issue for lots of people all around the state and around the country. And I'm going to be taking a really broad view of forest management as it pertains to fire severity. And I'm just going to we're just looking at the differences among different ownership types in California. And this is reflective of a lot of how the debate plays out. When there's really this conflict set up between these two broad styles, one being embodied by industrial timber companies, and one being embodied by federal, or should have included state, basically public land management. And the difference primarily is the intensity of management. Industrial interests of course, are seeking to produce timber and maximize profits, and so typically employ silvicultural strategies, which are very economically efficient and productive. In California, the most predominant of these strategies is even-age silvicultural management, typically with plantation strategies, clear cuts and the like. Whereas on public lands, they're trying to balance, obviously, a diversity of interests, a diversity of objectives, from recreation to conservation to some timber extraction, and the like. And you can see this pattern at a really broad scale throughout California. It's quite obvious from this satellite image, looking at a transect as we go from the Central Valley on the left in the east up to Lassen Peak. We go transition from an area that is predominantly managed by private industrial forestry operations to an area primarily managed by the Forest Service and then to the Park Service. And you can see at this really broad landscape scale that there is a significant difference in the landscape scale arrangement of fuels. In the industrially managed land, we have a lot of sort of patchy checkerboard type even-aged plantations. Once those trees reach a certain age, there's a lot of crown continuity. Many people would critique that and say that fuel continuity could lead to extreme fire behavior and therefore to severity. On the other hand, often on public lands, because there has been sort of a lack of intensity in management, people will say possibly that that lack of management has led to a sort of an unnatural state of tree density, tree health, et cetera. I'm not going to be looking at a mechanistic level at the different management practices. What I'm going to be talking about today is very zoomed out view, just looking at these different ownership classes. And so that brings me to the questions that I'm going to talk about today, and that this study is based around. The first being, how does the probability of high severity fire, conditional on fire occurrence, vary across ownership types in California? And so we looked at actually 3 different ownership types. We have the 2 that are sort of the focus of this debate that I've talked about. We have private industrial ownership. We have land that's owned by public agencies, state parks, national forests, Bureau of Land Management, et cetera. And finally, we have any land that cannot be binned into those categories, which I'm going to call other. Here I'm showing a picture of a Nature Conservancy property in the Eastern Sierras, but this also includes a lot of individual private timber owners, non-industrial timber owners, conservation nonprofits, et cetera. And basically it's sort of a reference class, though I'm going to mainly focus on the difference between private and public land. Now, because of the history of land ownership since colonization in California, what we have is this really complicated spatial arrangement of ownerships, wherein boundaries are not, or ownerships are not in these big chunks. Oftentimes there's a lot of boundaries, sort of a lot of intermixing and inholdings. And so that sort of immediately begs the question of whether or not any effects that we observe that are related to ownership actually spill over across those boundaries. So if we observe, for example, heightened probability of high severity fire on land classified as other, does a piece of public land near the border with that other land also have a higher probability of high severity fire? Essentially, does the management on each of these classes affect the fire severity probability on their neighbors' land? And so to address this question, we did a very large scale analysis of fires in California. We took any fire on which at least 40 acres burned on both private and public land to partially control for any effects of fire suppression, et cetera, that might be different on those 2 jurisdictions. That constituted 154 fires since 1985. And we only considered land that was classified as yellow pine mixed conifer. And in total, we ended up with a data set that included just under 1 million hectares or 2.4 million acres. And very similar, almost identical to what Stephanie talked about in her talk, we remotely sensed CBI values using the methodology in Sean Parks et al. 2018 to get 30 meter by 30 meter resolution CBI values for each of these fires. And we then classified those pixels into either high severity or low severity, moderate severity, depending or based on past analyses that have regressed them with on the ground plots of mortality and severity. The reason that I'm treating severity as a binary here goes back to my first slide where I talked about how the ecological and social consequences of high severity fire are very different. When we have that near complete mortality of the overstory, when we remove all the seed sources from the area is when we really get the worst effects. And so that's really what I'm going to be looking at and interested in. So to look at the actual effect of ownership and proximity to ownership, we fit a generalized linear model, the binomial link on severity, high severity versus not high severity. And the covariates that we included were first, the ones that we're mainly interested in for our study question, the ID of the ownership for each pixel. So whether it's owned by private industrial group, public agency, or other. We then included a variable for proximity to boundary of each other ownership type. So for example, a pixel of private industrial ownership would have two proximity values, one to the nearest pixel of public ownership and one to the nearest pixel of other ownership. We then fit basically a decay function by maximum likelihood to determine the spatial scale of that effect, and then did some averaging. And then we looked at some topographical covariates, essentially to control for any, statistically control for any, differences in things that we know to influence fire severity. And finally, we weren't able to include weather because we, at least in the initial analysis, because of the scale and the fact that it was very collinear with some of our other covariates, but just to make sure that we weren't sort of missing some big difference, we included a post hoc analysis of burn index's effect on severity. I forgot to mention that we also included fire ID as a covariate just to control for, again, any sort of unmeasured variation and suppression efforts, ignition source, that kind of stuff that's really difficult to measure or assess for each fire. And finally, a big issue with any spatial analysis like this is spatial autocorrelation, where basically the assumptions of the statistical inference are violated because pixels which are near each other are more likely to be similar in outcome than in other ones. So there's a violation of independence. And to address that, we used a technique called spatial block bootstrapping, which I won't talk a lot about, but just so you know that we've covered our bases there. So to get into some of the results, what we found, here I'm showing you the predicted probability of high severity fire by ownership and for a couple of the fires in the study, some of which you might recognize. And we can see that consistently, pixels which were owned by private industry were more likely to burn at high severity than pixels which were owned by public or private industrial land. Now you can also see that there's a lot of variation between the fires that's not explained by the model except in that fire ID covariate. And we can talk about why afterwards. But still, you see that consistent elevated probability for private industrial land. And now perhaps the more interesting result here, we have the effective proximity to other ownership types. And so just to explain this figure, because there's kind of a lot going on, everything in this part, this box, represents the predicted probability of high severity fire for a pixel owned by a public agency. And as we go from left to right, we're approaching the border with another ownership type. The yellow line shows us predicting or approaching a border with a pixel owned by other, and we see that the probability of high severity fire decreases. But as we approach the border with private land, we see that the probability of high severity fire, even on publicly owned land, is increasing quite dramatically. So that by the time we're within 1 kilometer, there's already quite a statistically clear difference between those that are near private land and those that are near other land. Similarly, or not so similar, for private industrial, we see here that on average, the predicted probability of high severity is higher, which gels with the last slide that I showed you. But as we approach either other land in the yellow or public land in the green, we're decreasing in the probability of high severity. And finally, for other, we see again that as we approach privately owned timberland, we are increasing in severity probability. And as we approach public, we decrease. So a couple of takeaways. In general, forests managed by private industry in California are more likely to burn at high severity fire than other forest lands, provided there is a fire. So this is all conditional on fire occurrence. Even on land owned by the federal government or other entities, areas near private industrial timberland appear more likely to burn at high severity. So that's that proximity effect. So possibly the homogeneous fuel structures frequently generated on private industrial land by practices such as even age silviculture are to blame for these trends, but I want to stress that further research is needed. I did not actually look at the management techniques. There was nothing in the model stating what actually happened on each pixel of land. And I think that that's really where a lot of research needs to be done, and a lot of research has been done. And finally, regardless of ownership, high severity fire incidence is increasing across the state. This is not a tacit endorsement of the management practices on either public or other land as far as fire severity is concerned. And clearly, we need to implement at a large scale fire mitigation treatments across the state, including prescribed fire and mechanical thinning. And finally, I'd like to thank my co-authors, Scott Stevens, Brandon Collins, Perry DeValpine, and Zach Steele, as well as the funding sources, Princeton University, ESPM at Berkeley, and the National Science Foundation. And with that, thank you very much for coming to my talk. And I think we should have time for some questions.
Excellent presentation. I'm also very impressed that that was done during your undergraduate degree. So congratulations on the upcoming paper.
Not completely. I finished it while I was a PhD student, but.
Excellent. Yeah. Well done. I'm sure that there will be some questions from the audience, and I think Brian has his video on for that purpose. So I will let him go first.
Yeah, awesome. Thanks, Susan. Great talk, Jacob, and really exciting and impressive analyses. One of the questions I had was if you've thought about on one of the last bullet points, you talked about the fuel structure as one potential driver of this. And I was curious, thinking about severity as a combination of like the fire behavior itself, as well as the structure of the forests that are on those different lands and how they're sensitive to even the same fire behavior. And if you've thought about pulling those two things out at all in this analysis.
Yeah, that's a great question. So we were very concerned with that at the beginning, that there might be some inherent bias in the severity measurements because young plantations might appear to burn at higher severity than other lands. And so what we did initially is we actually, and I didn't include this in the talk because I didn't really have time, but we looked at the effective stand age on fire severity across all this, and we actually found that there was no real relationship there. Possibly because the data was quite coarse. It's a little bit difficult to get that data, but I think it's definitely something to spend some more time thinking about. But we did definitely look into that and kind of decided that it wasn't really what was going on or underlying this trend, at least in this case.
Excellent. So Derek Churchill has another question for you next. Derek, we can't hear you yet. All right. Well, I'm going to beat him to it then, because I definitely had a question for you. And it has to do with California's kind of like goals to reduce emissions. I think probably what's happening in the industrial forest lands is they're leaving a lot of logging slash on site. And so that's a tricky one because it's basically pointing towards a different method of slash disposal. Did you address that at all in your discussion?
Not really. I wish that I knew enough to get into all of the carbon implications of this. It wasn't really within the bounds of the study, and also it was quite a short paper. By the way, I forgot to mention to look out for this in an upcoming issue of Frontiers in Ecology and the Environment. So no, we did not address that, and I don't want to give a answer because I don't think I'm qualified to. But
no worries.
That is a very good point. Yes, and I forgot to mention that slash, of course, is something that people often think is a driving factor, possibly of this type of discrepancy.
No worries. Yeah, that sounds great. And then Derek, I'm going to give you another opportunity if you can hop on. Otherwise, we're getting close to the end. Thank you so much for a great presentation. We appreciate it.
Thank you so much.
Right. All right. Well, we will be transitioning to our next presentation in 1 minute. And as Brad and Jamela are loading up their presentation, I'm going to give them an introduction. So Brad Washa is a state fuels specialist with the Bureau of Land Management, and I understand that you're about to have a big career change. And then Jamela Thompson is a master's student at Utah State University, and they're going to be speaking about fuel treatment effectiveness in Utah today. Thanks.
Well, thanks for that introduction, Susan. And we're doing a co-presentation here between myself and, yes, I am retiring at the end of the calendar year. And then Jamela Thompson and Larissa Yoakum has contributed to this presentation also. And Jamela will close things out at the end. So with this, within Utah BLM, since the inception of the National Fire Plan, we've completed about 1.3 million acres of treatments across the Bureau. Also, some of that work included state and private lands. The last 5 years, treating about 100,000 acres per year. These treatments have occurred across the landscape. We have about 23 million acres of surface land that the BLM manages within Utah. And this slide depicts where the treatments are occurring throughout the state. About 63% of the treatments, which are representative by the red triangles, are in WUI areas, and 36% are in non-WUI areas. This work has been accomplished with about $2.2 million in funding over the years. And as far as a breakdown of treatments, 81% of the treatments have occurred through mechanical means, either with chainsaws and piling, masticators like this one pictured here. 13% of those treatments have been prescribed fires, and 6% have been other treatments. And that could include chemical treatments, targeted grazing, and other biological means of treating the landscape. Sorry. So in 2007, started seeing some interactions with treatments across Utah BLM. This treatment is the Pine Creek fire that burned into the Cook Creek mastication project. You can see they kind of funneled it through with retardant. The fire was a crown fire in the pinyon juniper woodlands. Once it left the woodlands into the treatments, and you can see kind of the background behind the tree that's torching out, it went down to the surface. And this fire was 128 acres in size, burned from the north to the south. And, basically we're able to use that treatment to corral the fire itself, the Pine Creek fire. Also during this time had some literature coming out as far as looking at the effectiveness of landscape fuel treatments within the across the West, and this was a paper Rick Stratton did. This treatment was down by Cedar City, and the Ash Creek fuels treatment basically provided a foothold in a place where they could stop the Blue Springs fire from coming into the community of New Harmony. We started looking at, we had all these various examples of treatments, but cumulatively, do we have were we capturing that? So we initially started with just a spreadsheet, having people on an annual basis identify treatment, or if it was a treatment that a wildfire burnt up to and was
Hey, Brad.
to stop it. So we initially did that.
Sorry, Brad.
With a spreadsheet. At about the same time, the Pacific Northwest was also doing capturing this data, and we developed the fuels treatment effectiveness monitoring system, and a Forest Service and in Joint Interior, BLM, Park Service, BIA, Fish and Wildlife Service program that was developed to capture this. We have since moved on to the next generation FTM that has a spatial component to it, and that's how we're capturing this sort of data. This system does allow it does identify when you've had an potential intersect, and then the field does have to enter various elements to that. Throughout Utah, we've had numerous examples where fuels treatments have been effective, and in this example, the Ellerbeck fire was almost $500,000 in costs to suppress this 3,600 acre fire. And this fire, we had several hotshot crews, I think about 70 air tanker drops on this fire. Some of it was in a previously burnt area, some of it was in a newly burnt area. At the same time, the bunch fire started. We were able to keep that at 16 acres and basically within the footprint of an existing fuels treatment. These two fires were started by the same lightning storm that came through. And, when we modeled the bunch fire, had the fuels treatment not been in place through WFDS and a short-term fire behavior run, looking at 1,200 to 5,000 acres in one burn period for that fire versus putting two engines on the fire and a dozer to help in the suppression effort on that fire. This past summer had the Bear Fire that burnt into several of our project areas, including the Price Canyon and Ford Ridge fuel treatments. The Price Canyon project was in a ponderosa pine stand that had been encroached with mixed conifer in the understory. A number of treatments, including thinning, piling, pile burning, occurred within this project, and then understory burning subsequent to those treatments. These areas, the Price Canyon area, we did not feel it was safe to put firefighters in, and so we allowed the fire to burn through that stand. The Ford Ridge project, just adjacent to the Price Canyon project, the project was never fully completed. The intent was to try to have a high severity stand destroying type event, in part to encourage aspen regeneration. And basically the Bear Fire did that for us. When we look at the severity across the Bear Fire, it's interesting to look at that. And this next slide shows at the bottom, you can see the Price Recreation Area. Only 3% of that area experienced high severity fire, whereas in our other areas, we experienced a lot greater severity. The Ford Ridge had a 34%, and then mixed conifer that was in a non-treatment area had 45% high severity. So does show the resiliency of these projects, even though it didn't stop the fire. It did allow us to not put firefighters in there, providing for firefighter safety and resilience of the landscape. Same time that the Bear Fire was going on, the Pack Creek Fire was occurring. And this was down by Moab, Utah, early season June fire, and burnt into the Pack Creek development. And although we lost 4 primary residents and 7 outbuildings, there were many structures that were saved because of treatments that occurred in the area. Firefighters were able to engage the fire back off to safety zones and then come back in. It also, a lot of the landowners received grants to do treatments around their property. And the losses could have been much more significant in this fire had it not been for those treatments. On the public lands, both Forest Service and BLM, we had over 1,800 acres of treatments in and around the Pack Creek area. This past summer, 26 treatments were intersected. So again, either a fire started within a treatment or a fire burnt up to a treatment. And starting to see an impact of those treatments. Overall, since we've started collecting data, 314 treatments have been intersected. So the blue line is the number of treatments, and what this basically is showing is 14% of our treatments have been intersected or had wildfires intersect on BLM lands within Utah. And you can see across the state, it's not just concentrated to one area. We see that throughout our BLM lands of 23 million acres of surface management. So when I first got to Utah in 2004, we were experiencing significantly large fires. We were having fires in 2005, 6, and 7 of 200 to 400,000 acres of total wildfire acres burnt within the state when I arrived. But then we started seeing and starting to wondering cumulatively if our fuels treatments were having an impact. And since that 2007 time period, we've only had 1 year, 2012, where actually more acres have burnt in wildfires than we've had in fuels treatments. So we reached out to Utah State to say, hey, is this just an observation we're seeing in cumulatively what's happening on the ground, or is there something else occurring here? And with that, I will stop sharing, I believe, and hopefully, and Jamela can take over.
Right, I'll share my screen here. Okay, can you all see my screen?
Looks good.
Okay. Thanks, Brad. So as you said, my name is Jamela and I'm a grad student at USU researching fuel treatment effectiveness. So my study is broadly asking, how do wildfires and fuel treatments interact on public lands in Utah? So fuel treatment effectiveness can be measured in a lot of different ways, and it generally depends on the objectives of the treatments. So our statewide assessment includes a wide range of habitats and treatment types. So I'm approaching the question of fuel treatment effectiveness using several metrics. So first of all, I wanted to see how often fuel treatments are encountered by wildfires and if factors such as how long they've been on the landscape or their size affect their chances of being run into. We would expect that most treatments are not encountered by fire in their lifespan. So then when a treatment is encountered, I wanted to see how much of it is burned and if that's affected by treatment size. So in the next part of my study, I'll be comparing burn severity in fuel treatments in areas that were burned to nearby areas in the fire that were untreated. And then in the final part of my study, I'll be looking at some ecological health metrics in sagebrush steppe from field data that I collected last summer. Treatment effectiveness is more well studied and understood in forested areas. So I chose to survey mastication treatments in sagebrush habitat. I used paired plots in mastication treatments that were burned by fire and collected vegetation data in and out of the treatments. So I'll be using that to look at how fuel treatments affect health metrics that we're interested in, such as native shrub regeneration, cheatgrass presence, and bare ground. So today I'll just be talking about my findings for encounters and proportions. So the fires and treatments that were used in my study were provided by the Forest Service and BLM for the whole state of Utah from 1997 to 2019. Both agencies provided me with the spatial data for their completed field treatments and their historical wildfires. So I also supplemented these fires with some more fires from the Utah Forest Institute and monitoring trends in burn severity. There were 3,200 field treatments from both agencies included in the study, and beneficial wildland fires were excluded from the treatment data. I binned the treatments into subcategories that were similar between agencies. So the purple dots represent the count of the treatment type, and the green bars represent the cumulative acres for each type. And I found that thinning and burning treatments had the highest acreage, but lop and scatter and slash treatments had the most count of treatment events. So some areas received multiple treatments, with the maximum regimen having 18 treatments, which was mostly fuel break maintenance. So this is an example of an area in Utah that has like several multi-treatment areas, where the yellow represents a single treatment and the darker areas represent more treatments. It's kind of what I would expect to see in an area that's been repeatedly treated, which is a regimen of thinning and burning. So areas that had overlapping treatments were combined to identify 3,080 unique treatment units, and these units account for 1.2 million acres of land. There were fewer areas that had only a single treatment, but single treatments account for most of the acreage, and there were more units that received multiple treatments but accounted for less of the overall acreage. There were about 1,500 wildfires that were used in this study, and I also identified areas where wildfires burned repeatedly, and the maximum were in 2 areas that experienced 6 fires. So the footprint for fires in the state was 3.3 million acres. So encounters are pretty infrequent, but there are some shown here in these dark areas on the map. And a coarser scale 2016 study by Barnett et al. Found that nationally treatments were encountered by fire at a rate of 6.8%. And I found an encounter rate that was similar to this national average.
So to get the treatment encounter rates, I looked at how many treatments were encountered by fire, and that was 8.6%. And then on the other side of it, I looked at how many of my total fires actually encountered a treatment, and that was 7.2%. So here's an example of what the encounters kind of look like from just the spatial perspective. It doesn't really like tell us a lot just looking at this. So that's why I'm incorporating those other metrics of effectiveness so that I can more thoroughly describe effectiveness at the end of this, at the end of the study. So after identifying the actual encounters, I ran some generalized linear models to see if size and age of treatments affected their likelihood of being encountered. And both size and age had significant p-values and showed that larger, older treatments were more likely to be encountered, which makes sense because the longer a treatment is on the landscape and the more area it covers, it means it has more opportunity to be burned in a fire. So then I wanted to see how much of the treatments are burned when they are encountered by a fire. And so this histogram shows the frequency of proportion burned with high frequencies of complete burnovers and also high frequencies of low proportion burned in the treatment unit. And so I found that size significantly affects proportion burned, where smaller treatments are more likely to be completely burned over and larger treatments are more likely to have a smaller percentage burned. And I'm currently working on analyses to test how other factors such as treatment size, treatment age, and type of treatment and treatment regimen affect this proportion burned. So to summarize today, I talked about my encounters and proportions results, where I found that larger, older treatments are more likely to be encountered, and that after being encountered, smaller treatments are more likely to have a higher proportion burned. The next steps in my study will be a burn severity analysis to compare severity in treated and untreated parts of the fire. And finally, I'll be looking for significant differences between treated and untreated burned mastication plots for shrub regeneration, cheatgrass, and bare ground. So I'd like to thank my funders and collaborators from the Bureau of Land Management, the Forest Service, Utah Division of Forestry, Fire, and State Lands, Quinney Foundation, Red Center for Western Studies, Utah State University Ecology Center, Sage Step, and the Utah Forest Institute. I'd also like to thank my advisor, Dr. Larissa Yoakum, and my committee members, Eric Thacker and Jim Lutz, and my fire ecology lab, and my field assistant, Lauren Jones. And with that, we will take questions.
Excellent. Thank you so much. That was really interesting. So I'm going to just open it up for questions. And so far, it's worked really well for you to just turn on your video if you want to ask a question and then start speaking. I happen to have done quite a bit of field treatment effectiveness research too, so I have some questions just to kick us off. My main one was that I noticed that you had separate thinning and burning as separate treatments. Have you considered or already done some overlays to see where those would have been done in combination?
What I have right now is like a layer of all of the areas and all of their treatments that are combined and overlapped. So no matter what type of treatment it was. And so I know, like in the Barnett study, for instance, they combined the thinning and burning units when they noticed that, but I haven't done that. I haven't like separated that as a separate regimen.
Excellent. Yeah. I've appreciated doing that, kind of drilling down with the treatments and then kind of looking at time since harvest or time since treatment as something that you can say at each pixel of your analysis. So might be something to look at, but looks like you've got really great results. So yeah,
that's a good idea. Oops, I'm gonna stop my share.
Okay. Any other questions from the group? We still have 30 seconds or so for another question. All right. Well, I wanted to congratulate Brad on your retirement and thank you both for a really excellent set of presentations. We appreciate it.
Yeah.
Thanks, Susan.
All right. Okay, well, as we're loading the next presentation, I wanted to introduce Scott Ritter. Scott is a research associate with the Colorado Restoration Institute, and he's going to be talking about restoration and fuel hazard reduction treatments today. And I'm really interested in this one too. Thanks. And Scott, take your time because we're actually 1 minute early yet again. All right, here we go.
There you go. All right. Well, hopefully I think you guys should be able to see the correct screen. So thanks for that introduction. Yeah, I'm Scott Ritter with the Colorado Forest Restoration Institute. And I'm going to be talking today about a project that I worked on as part of my PhD at Colorado State University. Really looking at comparisons between sort of restoration style fuel treatments versus what you might think of or call a traditional fuel hazard reduction style treatment in terms of outcomes for both spatial stand structure and potential fire behavior. So right off the bat, I got to thank my I think that did automatically my co-authors and collaborators on this project, both here at CSU and the Rocky Mountain Research Station. So jumping into a little bit of background, none of this should come as new to any of you, but I'm just going to talk a little bit about the fire ecology and fire history in these forests that we're working in. So specifically, this project occurred on the Black Hills, which historically had relatively frequent fire regime. However, that regime was fairly complex in both the effects and sort of spatial outcomes of fires. Sorry, I seem to be automatically forwarding. So this regime created a large diversity of structures, single-age forests, really complex patchy forests due to both this regime as well as other disturbances, including mountain pine beetle. In this context, we got some nice historical photos for the Black Hills, especially that really show how these impacts to the fire regime have both reduced the heterogeneity inherent in those forest structures and just an overall densification of trees. So there's a really stark example here of what was a pretty patchy forest. It clearly experienced a variety of fires and then now is pretty much continuous homogeneous ponderosa pine. And I'll just highlight that in this talk, I'm going to be kind of focused on ponderosa pine, but I think the conclusions from this study are applicable to numerous forest types. Because we were working in the Black Hills where things are pretty uniform. And so these trends are clearly not unique to the Black Hills. A couple more historical photo sets here from both the Front Range of Colorado showing this loss of spatial heterogeneity and overall densification. As well as Oregon, this nice sort of matrix structure of meadows and openings and tree groups, isolated trees, and that sort of thing that are typically associated with historical structure in particularly the dry conifer and frequent fire type system. So this is sort of the background for the project and why we were asking some of the questions we were. So. We have these ideas that the contemporary forest patterns in many places with these increased densities and reduced variability come with, increased fire hazard, both potential effects and things like having large spreading crown fires that have both ecological and social impacts. Similarly, we see as you lose variability, you're losing the diversity of habitat. So it is reducing the potential species set that particular ecosystem can maintain, both the variety of understory species as well as wildlife species that rely on different forest structures as part of their life history. Especially in the Black Hills, as we've seen up there over the last decade or so, these denser, sort of highly competitive structures have really increased susceptibility to large scale outbreaks of mountain pine beetle. And this has also been seen in other forest types, but has had a big impact up in the Black Hills. And then, lower resilience to not only insects, but things like drought, just these highly competitive environments. So all these factors, suggest a need to treat, not only to reduce fire hazard, as we often think, but also just from a restoration, both of structure and function of these ecosystems, and think about how we can enhance both stand and landscape heterogeneity. So that was really the crux of this project, was thinking about how we can do things like reduce fire hazard, and meet some ecological goals, associated with heterogeneous structures kind of simultaneously. So this slide here is just thinking a little bit about how treatments have been approached historically, especially in the realm of fire hazard reduction. A lot of times, following this sort of framework laid out in Agee and Skinner that really calls for thinning from below and sort of space-based forestry practices that results in relatively homogeneous forest structures. And as you can see in this photo here from recent Scott Stevens synthesis paper, where these are basically pictures from either side of a road moving through a treatment, where on one side there was a traditional kind of thin from below spacing treatment that created a very homogeneous structure, versus another treatment that focused on creating groups of trees, potentially some more vertical heterogeneity by retaining more understory and sort of mid-story sized trees. And as we're moving forward and thinking more about treating for multiple objectives, not just fire hazard reduction, there's sort of a growing emphasis towards implementing these more complex treatments. And so this project was really about both evaluating silvicultural prescriptions to create these types of complex stands, and then kind of do some comparison in terms of potential fire behavior between these structures. So as I said, overall goals, looking at spatial outcomes, and really thinking about how managers can balance these sometimes disparate objectives, or at least perceived disparate objectives. There's some thoughts that when we're creating these really aggregated patterns, especially vertically complex forests, we may not be achieving the same amount of fire hazard reduction that you could through a thin from below space-based type prescription. So that's really the context for this project. As I said, this occurred in the Black Hills, mostly on the Black Hills experimental forest. But really we're thinking about forest structure, and I think that these have implications outside of the pure ponderosa stands that we were specifically measuring, and as we'll see, doing some fire modeling within. Very briefly, we installed a network of 1 hectare block stem map. So we went in and mapped every single tree taller than breast height, measured all their crown parameters and their spatial locations. And then we also mapped all the sound, all of the recently cut stumps. So we were coming in here 2 to 3 years post-treatment. So we mapped all the stumps and used those to reconstruct the pre-treatment condition, because we put all these plots in after the treatments had already occurred. So that's our general data collection there. And now we're going to jump into some results. This slide is sort of a summary of all of the results that we found in terms of spatial pattern. So there were 11 stem maps, and essentially we put in plots across this sort of perceived continuum from restoration to traditional fuel hazard reduction. And in this talk, I'm not going to go too much into the specific prescriptions that went into all of these, but essentially on the left side here in the restoration, was the treatment that was intended, and the outcome of it was to create the most heterogeneous structure, all the way over to the right where we had a much more uniform structure. So our small group retention treatment, as we called it, resulted in aggregated patterns. Mixed tree size groups means that within the groups there was a mixture of tree sizes, a large range of group sizes, and then some nice large openings as well. And then as we move across these 2 different free selection treatments, both had random patterns, small groups and medium-sized openings, but they really differed in the types of groups. So in the on treatment, we had groups that had mixtures of tree sizes versus groups with uniform tree sizes in the ghost off. And commercial thinning or traditional fuel hazard reduction was just a thin from below spacing. So it created a dispersed pattern where groups did occur. They were uniform sizes and relatively small openings. So I'm going to try not to go into too much detail in terms of the resultant structure, because we have all sorts of metrics we can look at. But essentially, these two figures here are showing the stand proportion in various either group types or openings. So this is just based on crown width. So these stands appear very open. But basically, you can see that in terms of isolated trees, that commercial thinning CT resulted in a lot more isolated trees than the small group retention, which was creating fewer isolated trees and kind of pushing them more towards groups. This is particularly evident in our group size distribution, where you see that essentially that small group retention had a small proportion of trees as isolated, and then a nice sort of distribution of small, medium, and large groups. Whereas the other treatments created some small groups and not so much in the large groups. So this is all just to give some context on how these treatments varied spatially. There's also some suggestions here for potential prescription development, in that the pre-selection treatments didn't create as large of a group as they may have set out to in their objectives, and some of that comes down to just how you kind of advise your marketing crews and really explicitly highlight areas where you want to create groups. So that's a little bit on the horizontal structure in terms of groups, and then thinking about how the vertical and horizontal structure are interacting within these different treatments. The top here is the height differentiation index, and without getting into too much, this is just an index that represents the variability within a local neighborhood for each tree within the stand. So how different is your height from your neighbors, to get at that interaction between vertical and horizontal complexity. And the real highlight here is that all the treatments did increase horizontal heterogeneity, but the commercial thinning, sort of traditional fuel hazard reduction, had the lowest height differentiation index, right? Just representing again that this was a more uniform stand, and this is also a suggestion that potentially there's less so-called ladder fuel within that stand, right? Fewer small trees underneath or nearby larger trees that they could potentially carry fire vertically into. And then the other plot here is showing within groups how variable were tree heights. So within our actual aggregated tree groups, once again, the same pattern, with commercial thinning having very little variability within its groups. You got some spatial statistics, and I'm going to try and move kind of quickly because I'd like to get to the fire behavior and leave some time for questions. But essentially just reinforcing that the small group retention treatment really did create a quite aggregated pattern. So these are pair correlation plots. Anything above 1 is essentially showing significant, or well, outside of the gray, is significant evidence of aggregation. So you can see SGR was aggregated across all scales. And if you just look at commercial trees, basically the aggregation only shows up from 5 to 15 meters, suggesting some kind of neighborhood effect or sort of dispersion, either mechanically between crowns or due to the way that thinning was implemented. And then looking at the distribution of nearest neighbor. So essentially just showing how SGR had, this plot on the left just shows a lot more area far away from trees, right? So larger openings as compared to the other 3 treatments. Okay, so the main point of all of that was to lead us into our discussion of changes to fire behavior associated with these different structural patterns. And the big takeaway for me, I've highlighted it here with those red arrows. Hopefully that's large enough, but you can see in terms of canopy fuel consumption, every single one of these treatments significantly reduced potential crown fire activity or canopy fuel consumption, largely due to this reduction in the overstory, as well as this dense understory cohort that did exist pre-treatment. So they're all successful in significantly reducing canopy fuel consumption and had relatively similar percentages. And then moving over to another important fire behavior metric, maybe more from an operations standpoint, but rate of spread. The big difference between these treatments that came out was that the small group retention, created these bigger openings. It had more grass fuels in the understory. And those big openings allowed faster wind speeds, as we can see on the bottom right here. So this is a vertical wind profile. I apologize, that did that automatically. With vertical wind profile, just showing faster wind speeds in the understory that was really driving increased mean rates of spread in there. So that's just a consideration that I'll talk a little bit more about. And then I just wanted to end on this fire behavior discussion. And I totally forgot to tell you what model I was using. This is all with WFDS, which is a coupled atmosphere fire model. And so everything was simulated in 3 dimensions. And so we can do these cool things like look at how the fire line develops over time, and essentially see how when we're creating more complex structures, that carries over to increased complexity in both the fire line in terms of its location and spread, as well as surface fire intensity across that fire line, right, which carries over to some ecological effects where we can see, comparing the commercial thinning to the small group retention, we see maybe some more patchy mortality associated with small group retention versus sort of random mortality. So that has some important impacts, thinking about the sort of ecological impacts of potential fire and stand structure moving into the future. So just thinking about larger scale implications, this was a stand scale study. And I think that sort of the main takeaway for me is that our findings really suggest a lot of flexibility when designing treatments. If you're thinning the canopy and overall increasing canopy base height, I think there's a lot of room for some management space in terms of how you arrange your trees and what sort of tree sizes you leave in there. Really suggesting you can manage for multiple objectives, both ecological and fire hazard reduction. And I think this suggests that when thinking about landscape scales, we know landscapes are highly heterogeneous across scales, and it doesn't make sense to implement the same treatment everywhere. And so I think that you can use treatments in combination and kind of have some confidence that all of those treatments are going to achieve your fire hazard reduction goals and allow you to increase heterogeneity at large scales. I guess I'll leave it there. One last piece was just that this increase in fire rate of spread in the really open treatments might suggest you want to think about near WUI areas. Maybe you are less prone to want to increase rates of spread due to the suppression implications of that. But there's this overall need to consider spatial context when selecting treatment types. So kind of rushed through the end there. Hopefully we got a little time for questions and just look at a couple of big trees.
Thanks, excellent presentation. I'm just going to open it up. I see a lot of people in the participation list, and if you want to unmute yourself or show your video, you can ask Scott some questions. And true to form, all of these talks are ones that are very interesting to me, so it's been very easy for me to come up with some questions too. So one of them that I had was, you mentioned that, some of the treatments opened up the forest understory to a little more grass cover. I wanted to know what you sampled in terms of understory fields and how those were input into your CFD modeling.
Yeah, that's a great question. So when we were laying this project out, we were hoping to build a spatial model linking basically overstory to understory fuel types. And so we did put in a network, and I kind of glossed over this, of essentially 80 fixed radius understory plots that we sampled. We didn't use fuel load, but just fuel type. So was it litter, grass, shrub, grass litter mixture. And we didn't end up building very strong spatial models. I think we just didn't have enough sampling power to do that. So in this modeling, we used a pretty simple spatial model that's been used in some other approaches where we related local basal area. So we looked at each individual pixel that we modeled, and depending on the local basal area, we either assigned it as litter dominated, litter grass mixture, or pure grass. And overall, that aligns with what we saw in the field, but it was a bit of a sort of modeling leap because our data wasn't complete enough to be able to actually build a true spatial model of the surface fuels.
Excellent. I'm going to wait for just a moment just to see if other people wanted to hop in, but I had to follow up as well. So I'll politely wait for other people if they want to chime in. Excellent. I get to go again. So I wondered if you've been in communication with Russ Parsons and Lucas Wells about their fast fuels inputs to CFD models. Does that sound familiar to you?
Yeah, I mean, I know Russ. I've talked to him about other projects before. I am somewhat familiar with that, but honestly, I haven't plugged in with him enough on how we could potentially be integrating that into some of our approaches.
Well, I might follow up with you and just talk about it, because we're doing the 3D fuels project, and that's why I'm mentioning the understory fuels. And I think that it would be really good to start thinking through how we think about these different treatments, how they influence the understory fuels, and how that then translates to fire behavior. So
yeah, absolutely.
Yeah, thanks for a great presentation.
Yeah,
all right.
Thank you.
Okay, so we're now going to move on to Don Radcliffe's presentation. And Don is a PhD student in Brian Harvey's lab at the School of Environmental and Forest Sciences at University of Washington. And Don's going to be talking about long-term trajectories of fuels in the dry forest of Eastern Washington. Thanks, Don.
Great, thank you, Susan. Can you see and hear me okay? Is the PowerPoint right?
Perfect. You're looking great.
Right. Great, well, thanks for the great introduction, Susan, and thanks everybody for the awesome presentations on fuel management from multiple aspects. So today I'm going to talk about some long-term experimental work that we've got going on, looking at the long-term effects of fuel treatments here in the East Cascades of Washington. And I'm going to rush through the introduction because I think we've seen a lot of these types of introductions in this session. But basically, fire suppression and indigenous fire exclusion have led to accumulation of biomass, especially in frequent fire forest types that historically experience frequent fire. And that leaves these forest types vulnerable to uncharacteristically severe wildfires. And so what a lot of us scientists and managers often prescribe are a range of field treatments, which have kind of been the subject of this session and a lot of presentations at the conference. Basically different combinations of thinning, prescribed burning, or similar techniques to reduce fuel loads, open up stand structure, and make these forests more resistant to a wildfire in the case that one should come through. And field treatments have been studied in a wide variety of ways, as we've seen in the session at this conference. One of the early studies looking at field treatments was this fire and fire surrogate study, which some of you may be familiar with, which is a coordinated distributed experiment that was set up in the early 2000s at 12 sites across the country, including 7 sites in dry forests of the West. And it was set up to experimentally test these 4 treatment types: control, prescribed burn, thin, and thin plus burn. And a ton of studies came out of the fire and fire surrogates study network, including, I've highlighted a couple of sort of synthesis papers that came out of it here, looking at fuel loads, stand structure, modeled fire behavior. And sort of at a really general level, the results of those studies showed that prescribed burning is generally pretty effective at reducing surface fuel in the short term, but doesn't tend to have much effect on overstory in the types of fire weather conditions that prescribed burning is carried out in. Thinning reduces canopy fuels, but creates activity fuels, basically drops biomass from the canopy, which goes down to the ground and can create some more intense fire behavior, as we had a little bit of discussion about earlier. And then thin plus burning treatment, kind of the 1-2 punch, not surprisingly, was pretty effective at reducing canopy fuels and then reducing surface fuels. So those are the short-term results of this experiment. And these sorts of issues have been studied from a huge variety of other angles. But this question of the long-term performance of treatment types and of all sorts of issues of field treatment longevity haven't been quite as well addressed as those short-term effects. But since the Fire and Fire Surrogate study was set up in the early 2000s, there are studies coming out now on long-term responses to those experimental treatments, including some fuel studies that we have here at the top, and just a sample of some of the studies of other response variables. And we're adding to that literature. So today, we're going to focus in here on the Mission Creek site, or the Northeastern Cascade site of the Fire and Fire Surrogate study in Central Washington, where I'm doing a chapter of my dissertation. And this is in dry, historically frequent fire, ponderosa pine, Doug fir forest in the East Cascades, kind of sandwiched in elevation between the high elevation Enchantment Mountains, as you can see there on the left, and the sagebrush steppe near Wenatchee, Washington. And the timeline of this Mission Creek site is, again, treatments were implemented in the early aughts along with the other Fire Surrogates sites. And it was bracketed by treatment or by measurement periods on either side. And short-term studies that came out of it included these studies on fuel loading and forest structure that came up with results that were pretty consistent with the broader Fire and Fire Surrogates results that we talked about earlier. One thing that caught my attention coming into this study was that these short-term studies found really high variance of a lot of response variables at this site, both within and between units. And then I had the fortune of being able to lead crews in long-term remeasurement of these plots in the summers of 2019 and 2020. And in between that short-term and that long-term measurement period, a wildfire kindly came along and burned up 4 of our units, or didn't burn them up. It was a low severity fire. But so while in an ideal world, we would have a nice balanced experimental design like this, where we have 3 units each of control, burn, thin, and thin plus burn. Each of those units being about 10 hectares and having about 30 plots. Instead, our study design looks something like this, where we have 1 control unit, 2 burn units, 2 thin units, and 3 thin and burn units. And we also sampled 2 sort of control plus wildfire units, and I'll include those results in the presentation today, but they probably won't make it in the paper ultimately because of the different timelines compared to the treatments. So we're going to use data from this experiment to look at this question that's highlighted. Today we're going to look at some preliminary analyses, and so we're not going to look at the full set of questions that we will look at for the paper, but we'll be pushing forward with lots of analyses this winter. But today we're going to explore how treatment type, pre-treatment condition, and site productivity at the plot level affect fuel loading and stand structure about 15 years after treatment. And worth noting that 15 years is roughly the fire return interval, historic fire return interval in the system. And so it's interesting to think about whether response to treatment is analogous to possible responses to historical wildfire. And as we go through the results, I just wanted to highlight that I've had help from lots of folks along the way. Some of these folks are collaborators, but lots of folks at UW here in my department, as well as the Washington Department of Natural Resources and the Forest Service. And then funding for this long-term remeasurement effort specifically has come from the McIntyre Stennis program, as well as the Washington Department of Natural Resources. Okay. So at a pretty general level, we went out and at 210 plots using the same plot locations and the same methods as the earlier measurement periods. For the most part, we measured a range of surface fuel variables and tree variables. And the surface fuel variables were measured on 2 Brown's transects per plot. And then I also really, again, wanted to quickly highlight help from lots of folks that came out and worked on our field crews. This was pretty field intensive work, and I was really lucky to have these folks helping out, and you should keep an eye out for them in the future because they're all really great. But they helped me collect a lot of data. And then so far, what we've done for analyses is we put them into generalized linear mixed models, which are going to help us get at that question that I posed a few slides back, looking at the effects of treatment type, pre-treatment value, and then a couple of topographic covariates that should act as proxies of productivity in this specific system. And then using random effects of unit, and I think the reason for using mixed models kind of is more clear from an aerial picture. Basically, we want to be able to harness information that we have at the plot scale. And the mixed models allow us to do that while controlling for covariance at the unit level. And this is an approach that it seems like a lot of the fire and fire surrogates papers that have come out recently are employing in one way, shape, or form. Okay. So I'm going to flash some of these results graphs across the bottom of the conclusions, but I just wanted to zoom in on them for an example real quick. So these are just the results of the GLMMs. You can see the coefficient values there are the dots. We've got 95% confidence intervals highlighted around them, and then fixed effects there scattered across the y-axis. So in this case, we're looking at the response of basal area to these fixed effects. And it looks like pre-treatment value and thin burn treatment probably have, you know, what we call significant effects on basal area. Important to note that the first 3 fixed effects are continuous and the last 4 fixed effects are categorical treatment types. So we can't really compare effect size or confidence intervals across them. And so we've done these kind of results for a range of surface fuels, litter, duff, fine woody debris, as well as a few stand structure variables. All right, so takeaway points. I think the main takeaway point for me in this preliminary work so far is that these pre-treatment values are really consistently coming out as important for predicting long-term response of a wide range of response variables. And it's sort of a humbling message to me that's saying that, you know, we're starting with the template that nature is giving us and that history is giving us, and that we're not resetting it when we're going out and we're doing these treatments, at least not in the long run, right? And that's not super surprising in these landscapes that are pretty variable and often pretty topographically driven, which applies to, I think, a lot of these dry forest landscapes across the West. That said, our individual topographic fixed effects didn't really show much of an effect on many of our response variables, which was a little bit surprising and something that we've been thinking about how to operationalize a little bit differently. As we saw in the basal area example, it looks like thin plus burn treatments produce persistently open stand structure into the long term, which is obviously really good from a crown fire potential standpoint. But one thing that our group is interested in this project and others is thinking about how that open canopy might in the long run affect the shrub response and the tree regeneration response and the surface fuels and the ladder fuels in the long run. There's this idea of a treatment intensity longevity trade-offs that we're going to explore in this project and others. And then thin treatments, it looks like those activity fuels that we saw in the short term from thin treatments seem to persist into our long-term measurement period. And we see stronger effects of that in the bigger fuel classes of surface fuels, 100-hour fuels, that would take longer to decompose after the treatment. And then really quickly, I've hinted at some of the future work that we're planning on doing. I think the big one here is kind of tweaking these generalized linear mixed models. The biggest thing that I'm excited to get a look at is treatment intensity at the plot level, because these treatments are actually meant to be variable across the unit, and they are quite variable across the unit, as we can see in Michelle's photograph there. And so we're working on pulling in some RDMBR data of burn severity and of bringing thinning intensity into the models, as well as bringing in a synthetic index of the topographic effects instead of the individual covariates that don't seem to be working super well, which may both be more effective and parsimonious in the model structure. And then we want to use an ordination as sort of a qualitative support of our results that we're getting from our models, to help us understand what kind of within and among stand variation we're looking at in our different stands, and how that might affect treatment response. So probably doing an NMDS analysis. And then finally, we're going to model fire behavior, fire intensity, as well as fire effects, so tree mortality, to just get at the question of whether these treatments in the long run are performing according to sort of acceptable management thresholds. And that's something that our agency partners have asked for. And so that's it for me. Obviously a ton of folks to thank, and I've been able to get a lot of their pictures into the presentation to highlight their roles in this, as well as funding sources I haven't mentioned explicitly yet. The School of Environment and Natural Resources and the College of the Environment, I'm really indebted to for funding me personally, and the Joint Fire Sciences Program for funding the original Fire and Fire Surrogates study. And with that, we should have some time for questions.
Excellent. Thank you so much, Don. That was really interesting. Before we open it up to questions, I just had to let you know that I took fire ecology from Jim Agee with Reese Lawley. And so I was completely there at the ground level of that research project. So it was very fun to hear the follow-up. So yeah, thank you. So with that, we still have 41 participants, which is very impressive on the last day of an online conference. So if anyone wants to pipe up with a question, no one's used really the Q&A. So people have just been turning on their video to let me know that they want to ask a question. True to form, I have some of my own. So, great. Here is, are you Robert?
Yeah, I usually go by Robbie, but Robert works too.
Excellent. All right, nice to meet you.
Yeah, nice to meet you too. Great talk, Don. I was just curious if you're able to account for fire weather or differences in fire weather in your analysis, because those plots are spaced out a bit and may have burned at different times. And I also noticed that the thin and burn site is right on the fire perimeter. So I'm just wondering if there's any thoughts about whether firefighters used it as an area to sort of backburn, or maybe that experience fire in a different way than some of the other plots. So yeah, again, great talk, and I'm curious to get your thoughts.
Yeah, thanks for those great questions, Robert. On the fire weather piece, in terms of the prescribed burning intensity, it did vary quite a bit across the different treatment units, and there was some of the units were burned in different years with different results. And so that's one of the reasons that we're trying to bring in that treatment intensity data, probably through RDMBR, although there's some scan line issues we're trying to work on, which I know a lot of you have dealt with. And so that's how we're trying to account for some of the differences in severity of the prescribed burns. And then that fire modeling, we are going to test results in both moderate fire weather, 80th percentile fire weather, which is kind of what the Fire and Fire Surrogate study was set up, with 80th percentile fire weather in mind, as well as more extreme fire weather in terms of our modeled results. And then this unit up here on the very perimeter of the fire, it's actually like right along a pretty steep ridge top. And I believe they did some backburning off of it, but the the fire did stop pretty much right at that ridge top. We had to not resample two of the plots that it looked like the wildfire might have got to, or that were just like right along the edge of that. But it's a really strong, really distinct north-south divide in forest structure and wildfire response there. That's not immediately obvious from just looking at the map here. I wish I had a photo ready for you because it's pretty cool looking actually.
Any other questions from the audience? I have a comment. I was going to confirm that I've really noticed in both thinning and underburn treatments, especially repeat treatments and reburns, that especially on moisture sites in the East Cascades, flammable shrub fields are coming up more and more. And it's kind of fascinating that first treatment, whether it's fire from lightning or from humans, seems to kick back to timber understory. But then I have been noticing this flammable shrub layer is becoming more common. So it'd be really interesting to see how you guys tease that out.
Yeah, it's something that we've thought a lot about in this project and others. Like I've mentioned, it's something Derek Churchill, one of my major collaborators, is really interested in. And the results are pretty variable at this site because of how variable the productivity can be with the topography. And so it'll be interesting to look at moving forward.
Right, absolutely. Well, thanks again. We're going to move on to Brian Harvey now. Okay, as Brian's loading his presentation, I wanted to introduce him. So Brian is an assistant professor with the School of Environmental and Forest Sciences at University of Washington. And just to change things up again, up a little bit for this session, he's going to be actually talking about forest fires in the West Cascades. Thanks, Brian.
Awesome. Thanks, Susan. And just quick sound check and visual check. Everybody see okay and hear okay?
It looks great.
Okay, awesome. Well, yeah, this is, thanks for the introduction, Susan. And this has been a fun session. And I feel like we've been sort of marching slowly from the Southwest through the sort of Middle Rockies. And now we're in the Northwest. And I'm going to take us over the final hurdle of going to the Northwest onto the west side of the Cascades. So along with my collaborators, we're going to dive into several different projects we have going on in a fire regime where high severity fire is more business as usual, as opposed to something that we're necessarily trying to change, like in these other talks so far. So first off, I do want to give credit where credit is due. This is a talk that includes a lot of different work jointly done by lots of collaborators, supported by several different funders, graduate students in the lab, who you'll see call outs to some of their talks and posters in this conference, as well as lots of folks who've been helping in the field over the last 3 years while we've been working on this. So as we've been hearing a lot about in this conference, and I feel like that it's sort of like we just keep cranking it up more and more, and it's sort of now cranked to 11 if it wasn't already there. There's a lot of concern about escalating fire activity and what that means for forest ecosystems, particularly in drier and areas where there have been more opportunities to look at fires, and really trying to understand if increasing fire activity and changing climate is essentially having us depart the envelope where the resilience mechanisms of forests are going to continue to be effective. However, there are some spots where we just really haven't had as much of an opportunity, at least in the contemporary record, to ask these kinds of questions, particularly in areas with very long intervals between fire regimes, such as the Pacific Northwest on the west side of the Cascades, where we have old growth forests that we know were born of fires of a long time ago, but we haven't really had an opportunity until recently to see what unfolds immediately following those fires or what those fires are even like. And so the region I'm going to be talking about today is what we're calling Western Cascadia, in this series of projects and grants that are supporting this. And we're essentially talking about west of the Cascade Crest in Northern Oregon and in Western Washington, in a fire regime that is generally understood to be a long interval and high severity fire regime, at least in terms of the fires that affect a broad swath of the landscape. And these are high biomass forests in extremely productive locations on the wet and west side of the Cascades. We know that fire has been a part of these forests for a very long time. As long as humans have been here, Fire has been used and continues to be used today as a management tool to promote culturally important plants, such as huckleberry as one example. We also know in the paleo record, as well as in the dendrochronologically reconstructed record from cohort establishment, that there's some suggestion of fairly large stand replacing fires with big patches of stand replacing fires that have occurred in the past. Documentary records also suggest that these things are part of the characteristic regime in this forest. And so the Yakult burn being one example of that in 1902, that burned slightly greater than 200,000 hectares in a matter of a few days on the west side of the Cascades on both sides of the Columbia River, mostly during a period of extreme east winds in early September. And from the maps from fires like that were drawn, as well as some photographs of those landscapes, we get the idea that fires like this are potentially part of how this system operates. However, we don't really have a lot of critical information with the tools that we have today, where we study things like heterogeneity in fires, which we know to be a really important mechanism of how fires operate, as well as mechanism of resilience and response to forest fires, because we haven't had many in the satellite record on the left-hand side you see there, as well as there being a lot of fragmentation of the puzzle pieces that we would otherwise be able to use in this landscape due to historical legacy of the last 100 years of timber management in this location. So a lot of those puzzle pieces have been removed. We also have most of our understanding of how post-fire resilience unfolds in this forest through retrospective studies, where we go into a forest today that has evidence of past fire and we try to reconstruct what happened in the past. And through lots of work like that, there's been a pretty broad understanding of at least how we think these forests operate immediately following fire, as illustrated by this awesome illustration by Bob Van Pelt here. But we don't really have, again, an understanding of in real time how these mechanisms of resilience unfold. And so things like post-fire vegetation dynamics that may be fairly transient and don't leave that permanent record are hard to test in that retrospective lens, as well as what the effect of these fires are in terms of changing things from pre to post-fire carbon, or thinking about disturbance feedbacks like fuels and the potential for reburn in these landscapes. So recent fires have now provided an opportunity to do that, including now the 2020 fires that burned during the anniversary week of the Yakult burn during another period of these extreme east wind events, and now present an opportunity to look at this. And so in a series of different projects with several collaborators and partners, we're working to understand what we're calling the driver's characteristics and effects of fire in Western Cascadia. For brevity today, I'm just going to focus on these two components of it, one component of the characteristics and several components of the effects of fires. And so let's dive in first to look at the burn severity patterns as one component of characteristics of these fires. This is a project with the collaborators that you see there, and we're essentially asking, first off, what are the characteristic spatial and landscape patterns of burn severity here, and how do they differ between large and small fires, particularly when we're thinking about east wind driven versus non-east wind driven events in this landscape. Our east winds up here are kind of our northwest variant of what we think about like the Santa Ana winds in Southern California. And so we're interested in not only just characterizing those patterns, but then also thinking about how those patterns are driven by other things like topography and fuels, perhaps differently, whether it's an east wind driven fire or not. And so we know that this measure of resilience, this measure of fire characteristics is a really important ingredient for resilience. Heterogeneity in fires sets the template for lots of different post-fire ecosystem processes, particularly when we're thinking about stand replacing fire, where it's the hardest kind of reset when a fire occurs. And so in this part of the project, we're characterizing our stand replacing path structure in these using methods that we've been applying in other systems over the years, as well as recently adopted methods from Sean Parks with Google Earth Engine, and from a alum of our lab, Saba Saberi, where we're calibrating burn severity maps to on the ground field measurements that we have, and then characterizing at the scale of almost 36 individual fires, as well as over 7,500 individual patches, the spatial configuration metrics of stand replacing or high severity fire here. So today's talk is just going to focus on one dimension of that, and essentially how these patterns differ between fires that were east wind driven or not. I don't have time to go into the topography and fuels part right now. So how we're characterizing whether these fires were east wind driven or not is a pretty brute force approach right now. We're looking at the burn progression maps using the Sean Parks code from 2014. Basically, the 2020 Beachy Creek fire is a great example of an east wind driven fire. You can see that it started on the east side and blew to the west, and actually blew mostly downslope during a period of sustained east winds. The 2015 Goodell Creek fire in North Cascades National Park is a good example of a not east wind driven fire. It was driven by the prevailing west winds and basically burned upslope and was topographically driven for most of its burn severity patterns. So what are we seeing at the fire scale? Let's take a look at this. A broad range of proportions stand replacing, as well as a broad range of fire sizes, but they kind of fall into two dimensions, and that is in these small fires, which are typically not east wind driven, we're seeing a really wide range in proportion burn severity. But then when we get into the larger fires, which are typically the east wind driven fires and the blue dots there, we see a convergence on severity patterns that is really right around this. About half the fire is burning as standard placing or high severity fire. And that has really big implications for the spatial configuration of that standard placing fire, because if you have a consistent proportion and you're just increasing the landscape size, you're going to have very strong effects in terms of very large and simply shaped patches of high severity fire, as well as lots and lots and lots of core area within those patches that's very far from live tree seed sources. So at the patch scale, there's another interesting finding that I'd like to share right now, which is that similar to lots of fire regimes that are organized by these kind of power law distributions, most of the patches are extremely small, smaller than 1 hectare in size, but they account collectively for a very small fraction of the landscape. Whereas 12 single patches that are larger than 1,000 hectares in size, all from 5 different east wind driven fire events, account for greater than 2/3 of the total standard placing burned area. So that tells us that the patches that are being produced in these often very short duration events of these large fires are affecting most of the burned landscape and are going to have a very lasting legacy on that landscape, similar to a lot of the historical fires that we know from some of those past records. I'm just going to give a quick shout out to Michelle Bonaducci, who's a PhD student in my lab and has a talk that's on demand, live streaming, if you want to check it out, where Michelle is taking some insights from the spatial patterns that we're seeing in the Western Cascades and then comparing that to how fire size and different configuration metrics of standard placing fire are arranged across different fire regimes, where we have a lot more data to be able to ask, how can we actually start to forecast what the future might hold in terms of fire size and spatial configuration of standard placing fire in this fire regime, essentially by harnessing the fact that we have a lot more data elsewhere and can learn from that and apply it potentially to this fire regime. Okay, I'm going to wrap up this talk talking about some of our insights on the post-fire forest ecosystem response here. And so this is a broad collaborative team of folks at UW, at the DNR, as well as at the Forest Service Pacific Northwest Research Station through the Westside Fire Initiative. And we're tackling several key questions about post-fire ecosystem response that I'll talk about briefly here. First, looking at two critical indicators of post-fire resilience with the post-fire vegetation dynamics. Post-fire tree regeneration being a critical mechanism, obviously, to have a forest at one point in time return back on these landscapes that have burned, as well as early cereal plant communities. And both of these are really interesting to think about in the context of this fire regime, because some of the evidence of what might have unfolded following past fires could be long gone by the time we go into a 300 or 400-year-old stand. And so being able to see this in real time and track it in today's environment is an important indicator of post-fire resilience to pay attention to. And then also thinking about the carbon consequences of above ground woody carbon in these fires and how fire has potentially changed the carbon distribution across the landscape. And then one person's carbon is another person's fuels. Interestingly, prior to the last several fire years, most of the area burned on the west side of the Cascades in the last 100 years was within the perimeters of these two large fire events about 100 years ago. And so this idea and concern about reburns is pretty big on the west side, and trying to understand the fuel dynamics and mechanism of that is part of our focus here. So we're looking at this through a network of field plots established across the region, broadly arranged by forest elevation zone, stand age at the time of fire, so the pre-fire stand conditions of either early seral, mid-seral, or late seral forests. And then we're looking at this in unburned control plots, as well as less than standard placing fire and standard placing fire at a range of distances to the edge of that patch in those standard placing fire areas. We're doing this across as many fires as we've been able to sample over the last several years. We started this in 2019 with the post-fire sampling. We actually started measuring burn severity in these areas in 2018, and we'll be sampling at least through next year to be able to set up 165 plots as our target minimum number. We've got 90 of them so far, and then in those, we're basically measuring a pretty comprehensive suite of response variables in a 1 hectare plot. And these are long-term plots that are permanently monumented to be able to sample them at regular intervals following fire in this location, or in each of these locations. And we're particularly interested in testing several expectations about the effects of pre-fire stand age. So you can imagine that we go back to this Bob Van Pelt illustration of successional dynamics. If a fire were to occur in a young forest, or a sort of mid-seral mature forest, or an old growth forest, we might expect very different responses on each of those different dimensions that I shared a second ago. And so that's one of the focal things that we're really interested in testing here, because the landscape mosaic on the west side contains young, mature, and old forests that are inevitably going to burn at some point. And so here are some example results, and again, pointing to some of the posters that you should check out if you're interested. So Madison Laughlin is a grad student in the lab, and she's looking at the post-fire tree regeneration dimension of this. And Madison's results so far are showing a pretty strong effect of pre-fire stand age, not just on the total post-fire tree regeneration, but also the composition, to where we have greater numbers and a much greater diversity of species that are coming back following fire if the stand was a late seral old growth versus an earlier stage of development when that fire occurred. Conversely, for the understory plant communities, we're seeing a slightly different effect. And so Liliana Rangel-Para is a graduate student in the lab who had a poster this week as well, and is finding, in this part, we're finding that the post-fire plant community is actually more diverse and more evenly distributed in the early seral stands that burned versus the mid or late seral stands that burned. And then finally, Jenna Morris is a grad student in the lab and is looking at the woody carbon and fuels and reburn potential of these stands after these recent fires. And Jenna also had a poster this week, poster number 2 there. Similarly, very strong effects of pre-fire stand age. So here, pre-fire stand age is each of the vertical rows here. And so as we're going up in stand age, we see a shift in the total woody carbon, as well as the coarse fuels and fine fuels that are coming back following these fires. So some of the insights from the post-fire sampling so far is that there's a very strong suggested effect of this pre-fire stand age, and that when you have younger stands that burn, there's slower tree regeneration, lower diversity of the tree component, and lower fuels and carbon that are left behind, but actually a higher species diversity of the otherwise early seral plant community. And then on the other end, when old growth stands are burning, you have quicker tree regeneration, quicker diversity of the tree component, and higher post-fire carbon and fuel. You actually have a little bit lower of a early seral plant community than when those early seral stands burned. Overall, the diversity is pretty high in all of these areas. I just want to note that too. Okay, and then finally, more to come on this. This is the first leg of the relay race here. We're going to be remeasuring these plots at regular intervals throughout our career, and this is only one step of the very long relay race in these forests that is going to be needed to really unpack this understanding through time. Summing it up for now, spatial patterns really different in terms of the burn severity patterns, whether a fire was east wind driven or not, and those extremes that are created during those high severity patches in those east wind driven fires really rule the landscape and set that landscape template for forest recovery for potentially centuries to come, depending on when the next fire occurs. And so far, many of these post-fire indicators of resilience that we've been looking at are very strongly shaped by the pre-fire stand structure legacy and the age of the forest at the time of that fire, as in addition to things like distance to seed source that is corresponding to that landscape pattern of fire. And with that, I want to say thanks. And once again, thanks to our funders and supporters on this, and love to take any questions if there's time.
Thank you so much, Brian. That was quite the overview. You guys have been very busy. So we have about 1 minute for questions. And then I'd recommend that for those of us that want to attend the plenary, we hop right off. So thank you all for such a rewarding special session, or actually general session. Any questions? We really do have time for one if you wanted to get in there. Well, I will just say, Brian, that I'd love to have a longer conversation with you, because I've been pretty fascinated by Andrew Marshall's work in the South Cascades and how there was a lot more fire in these supposed old growth forests that might have been 700 years old than we previously gave credit to. It'd be very interesting to bring that set of questions north too.
Yeah, absolutely. And Andrew, as part of that project, they are sampling up further north too. And so I think we'll be able to get some insights into some of those perhaps hidden, latent fire scars in the landscape. That'd be really cool.
All right, well, thanks again, and have a good weekend, everyone. Okay, bye.
Thank you, Susan. I want to thank all of our speakers for sharing your expertise and experience with us today. This session will be available in Whova, our conference app, within 2 weeks after the Congress ends. Be sure to join us at our closing plenary session starting right now. This session will feature our special award announcements and keynote speaker Paulo Fernandez, Associate Professor at the University of Trás-os-Montes, and Lenya Quinn Davidson, Area Fire Advisor for the University of California Cooperative Extension. To choose this session, go to the Agenda tab to the left of your screen, click Sessions, and click the main session title to join. Thanks again to our speakers, and enjoy the rest of your day.